Um, the very last thing we did last week was we spoke about the existence of this thing called an exponential relationship, which is where we have a graph like y equals such and such x, but instead of having the x being multiplied and divided and so forth down the bottom, the x actually sits up there in the power. And what that does is it produces this type of graph which is very, very fast growing. So this is what's so scary about pandemics or whatever, is that they exhibit this type of growth called exponential growth, where the power of where the x is sitting up there in the power. So it is the x is telling you how many times is the base getting multiplied together. So if we draw up a table of values for this relationship here, 3 to the x, then we get these sorts of values here, and it makes sense. 3 to the 0 gives us 1, 3 to the 1 gives us 3, 3 to the 2 gives us 9, etc. And for the negative powers, remember we interpret those as being 1 over. So 1 over 3 to the 1, so that's 3 to the negative 1, gives us a third. So 1 over 3 to the 1. 1 over 3 squared gives us a ninth, and that's what 0.111111111111111 is, and so on and so forth. So we can get all these values here, and then we can say, once we've set that up, we can say, well, what would it mean to talk about maybe 3 to the 2.157? Or some strange number that's not a nice fraction like a half, not an integer certainly, but just any old random number. Well, what we could imagine doing is taking these points that we've constructed for all our integer values of x and joining them together in a smooth line, joining them together in a smooth relationship here. So what we end up with then is y equals 3 to the x, and if we want to know what is y when x is equal to, let's say, 3.12, well, then we can just go to our, we can go along our graph here until we get to 3.12, and we can find that point there. So this is allowing us to extend our definition of powers to not just integer numbers, not even just fractions, which we interpret in terms of those roots, but to any number at all that we can throw up there as an exponent, as our index. Okay? So the other thing it does, though, is it gives us a really powerful graph for modeling quick growing processes, or as I'll show you in a moment, processes that die out as well. One thing I want to show you here, I'm just going to get rid of the table of values now because we can replace it now with this smooth graph. One thing I want to show you is, I'm just going to match a parabola, put a parabola on top of that. And if we look at our parabola here, it's got the same y-intercept. It goes through, when x is 0, it's also 1 because it's 5x squared plus 1. My apologies. Just like 3 to the power of x is when x is 0, 3 to the 0 is 1. So they have the same y-intercept. And at first, it really seems like the parabola is growing faster. It streaks away from the exponential, and it stays ahead. And that's because it's got that big 5 out in the front, multiplying. Every value you get for y gets multiplied by 5, so it becomes really big. But my contention for you is that it doesn't matter how big you make this number, an exponential will always catch it. That's the logic of exponentials, is they grow so fast eventually that it doesn't matter how big you make that number. So if we zoom out of this graph, we're going to find there is eventually a point where our exponential takes over, and then it never looks back, and it just out. And it's almost perfectly vertical by the end here, whereas our parabola is still growing more gently. And I could extend this argument. I could make my parabola really, really big. I could make it like 100. So it's way, way faster growing than our exponential, but there's still going to come a time, it might be a little bit further into the future. They're getting closer together. They're getting closer together. There comes a time when the exponential, just got to zoom out further, when the exponential blasts past our parabola and is on top of it again. Okay, so it doesn't matter how big you make your parabola, how tall you make your parabola, how skinny you make it, an exponential will always catch it and go past it. And that is just the basic logic of exponentials, is they grow incredibly fast. Sorry if this is making anyone seasick. I'm going to get there soon. We're nearly there. We're nearly there. Okay, hold on. I've just got some chat that I want to check on the thread. So the parabola always has that sort of same shape like that, and you can make it really tall and skinny, but you'll never make it skinny enough that it's going to outrun the exponential eventually. And actually, none of the graphs we've ever come across will grow as fast as an exponential. Teresa's just asked there, how precisely can we talk about this? I'm speaking pretty loosely at the moment, but the point being that these exponential graphs just grow. At first, they seem to grow pretty slowly, but they take off and they end up going pretty much like almost vertical up. So a tiny little change in X causes an enormous change in the Y value. I'm not sure what that was, but that's okay. So we might want to know what's the general equation. How can we write down literally any exponential, right? And the way we're going to do that is we are going to use this equation here. Y equals A times, and I'm going to use 2 here. You can actually use any value here, but I'm going to use 2. And then X divided by something, right? And so you might wonder what that divided by something is doing there, but I'll talk you through how to interpret this graph here. Okay, so this is our general way of writing any exponential that we like. Okay, so first off, the A, what that's doing is that's giving us an initial value. So if we think about putting X in as 0 here, then we're going to have 2 to the power of 0. So all of that is going to be 1. So if we make our big A there 10, then our graph is going to start from when X is 0, the value of Y is going to be 10. Okay, let me just put A on the board. Here we go. Okay, so that's our blue curve here that we're talking about. So A is going to tell us what this y-intercept is going to be. Right? It's going to give us the value of our exponential when the exponential itself is getting raised to the 0. Okay, the next thing we might wonder about is, okay, we've got this 2. What is this 2 doing? It's saying for every step, we're doubling. Okay, so every time we sort of increase the exponent by 1 up here, we're going to be doubling the value over here. And so at the moment, we've set t here to 1, so we can just treat this as 2 to the power of x. So when x is 0, we've got 10. When x is 1, we've got 20. And when x is 2, up here, we've got 40. So we're just doubling every time x moves forward. Right? And if you go the other way, if you go into the negatives, then 2 to the negative 1 is a half. So it's going to be a half of 10. And that's going to put us there. So negative 1 gives us 5. 2.5. I'm very bad at doing mental arithmetic at the moment. 5, 2.5, 1.25, 0.675, just halving and halving and halving as we go backwards, doubling and doubling, doubling as we go forwards. Now, what does this t here do? This t here just makes that exponent either more extreme or less extreme. So if we put t equals 5 here, then what we're doing is we're saying in order to increase the exponent by 1, we need to actually increase x by 5. So it's 10 at x equals 0. It doesn't get to 20. It doesn't double until x equals 5. If we set t equal to 8, then it'll take x has to be 8 before we get 2 to the power of 1. So our graph doubles when x equals 8. So you can think of t as your doubling factor. So how often does this thing here double? So if we think about something like compound interest, put some money in a bank and get some interest over time, this t here is really what you're most interested in, because this is telling you how long will you have to wait before you double your money. Okay, so if this exponential here represents your money over time, you want this t to be as small as possible. If we make this t 0.1, say, so we're only going to be dividing by 0.1, then we get really, really fast growth. We get something that explodes upwards. All of a sudden it starts at 10, but when x equals 0.1, it's already at 20. Okay, so that's what exponential graphs look like. There's a few things to say here. The first is that, let me just make t a little bit more well-behaved again. Let's make it 5. Now let's make it 6. There we go. So it's a little bit gentler when that big T is large. So it doubles when x equals 6. A few things to say. One is that if you make the original a value a negative number, then maybe just take a moment to have a sort of a silent think about what you think will happen if I make a negative number. So we're going to multiply our exponential bit by a negative number instead of a positive one. Hopefully you've got your thought in your head. I'm just going to zoom out of this graph a little bit. Okay, so I'm just going to make a negative now. So let's make it negative 5. So when we start with a negative number, we're going to be taking a negative number and then we're going to be multiplying it by a bigger and bigger value. So it's just going to get more and more and more negative. So putting a negative number out the front actually flips our graph over so that it looks like this. Okay. Now I want you to think about, and maybe this one's a little bit harder, so I'm going to make a positive again. Let's make a, that'll do. Okay, now I want you to think, what happens if I put a negative sign up the top here, in front of that x? So I'm going to reveal it in a moment, but just have a think to yourself. Okay, I'm going to stick that negative sign in here. So if we have a graph with a negative sign up here, well then, we actually reverse it in this direction, in the horizontal direction. Now, why would that be? Well, now we're saying as x gets bigger, we're going to a more and more negative power. So first we're putting t to the power of -1, then -2, then -3, then -4, and so on. So we're going to higher and higher negative powers, which means we're doing 1 divided by bigger and bigger and bigger denominator. So as x gets bigger and bigger, our graph gets smaller and smaller and smaller and starts to get closer and closer to 0. Now it'll never quite get to 0. There's a question in your exercises this week about why, so I want you to think about that for yourselves, but it will never quite get to 0. Okay, so that's exponential graphs, and that's actually what you need to do this week in 3J. So I've done things in a kind of reverse order. So those are your exponential graphs, and I want you to think about what those look like. I think we pretty much always make you do to a base 2, and the reason for that is it doesn't change anything particularly, but it just makes things a little bit easier to get your head around. The other thing I want you to do is actually solving exponential equations. So these are solving equations where we have the x up there in the exponent, rather than being something that you're able to just rearrange and solve for. So that's sort of where we're going to spend the rest of today's lesson, is on actually solving exponential equations. So, and I've got a range of different ones here. And as we move from left to right, and there's actually one on another page, as we move from left to right, these get sort of more and more difficult and require slightly different skills. But all of them, notice, all of them, we're unable to just rearrange for x. We need to use some sort of trick in order to get that x from up there at the top and down. Okay, there's no, well, at the moment we don't know the trick that lets us sort of reverse putting an x up to a power. That's not something we know how to reverse yet. Okay, so I'm just going to take you through one by one how to do these problems here. The first level of complexity is, well, obviously, by definition, is the easiest. And that's just where you just have something, a base to a power equals, and it's some recognizable power. So 2 to the x equals 8. You just have to rack your brains a little bit and say, what do I have to raise what do I need to raise 2 to get 8? And you can look at that and you can be like, 3. So x must be 3. Okay, those ones can come in a range of varieties. You might have 4 to the x equals 256, and I hope I've got that right. And you might not know that one off the top of your head. You might not know your powers of 4, but literally all you have to do is just look at it and go, okay, well, wait a minute, 4 times 4, that's 16. And 4 times 4 times 4, okay, that's 64. And 4 times 4 times 4, 64 times 4, oh, that's 256, yay. So how many times did I have to multiply 4 by itself? 1, 2, 3, 4. So x must be 4. Okay, so those sorts of ones, pretty straightforward. If you suspect it might just be a power of that same base, then you're golden. Okay, next level up. Next level up is where the power has an x in it, but isn't just x. Right? It's x written in some other way. It's some expression involving x. The trick to these ones is to write the right-hand side to the same base as the left-hand side. So you actually don't look at the left-hand side for a little while at the moment. You're just going to leave that as 6 minus x, 6 to the minus x. And what you're going to do is you're going to try and write this right-hand side as 6 to the power of something. And once again, just using the same sort of technique you used over here, where you're just saying, okay, what would I have to raise 6 to get that thing? Okay, you stare at it for a little while. Eventually, you're going to see that that's 6 cubed. Okay, if you never get to that step, if you're never able to see that, then you're actually dealing with one of these more difficult ones over to the right. And I'll give you the techniques you need to solve those later. But if you can see that this is actually a power of the same base, then you go ahead and you write it as that power. And then what we do is we're going to equate powers. So the only way that 2 powers of a number can be equal is if those powers themselves are the same. So negative x must be the same as 3, which means x must be negative 3. Okay? Hopefully that way is pretty clear. So the trick there is just to, for the meantime, just ignore that left-hand side and try and rewrite the right-hand side to the same power, and then to set those powers equal to one another. Okay, so we call this equating powers. Okay, we're going to use this equating powers trick again over here, but you'll notice there's a little bit of a problem, which is that now we have x's on both sides, but that's fine. We're just going to use the same idea, which is we're going to write both sides to the same power. So we're looking for a common factors between this side here and this side here, the bases on the two sides. Now in this case here, 125, well that is 5 cubed. So I'm just going to leave this left-hand side. 2x plus 7 is equal to 5 cubed, x minus 2. At this point, you're going to have to use your index laws. So we've got a power raised to another power. So we multiply the powers. So we get 5 to the power of 3x minus 6 on this side, and 5 to the 2x plus 7 on this side. And what do? We just equate powers. Going to get lazier and lazier at writing that each time I write it, I think. So we're going to have 2x plus 7 is equal to 3x minus 6. And then we just go from there. So we get 13 equals x, and we are done. Okay. Can I get a thumbs up or a thumbs down if you, a thumbs up if you would like me to move on, a thumbs down if you want to see one more example of this technique here. Okay, I'm seeing mostly thumbs up, but I'm seeing a couple of thumbs down. So I'm just going to do one quick one. Let me do, I'll just do one quick one here. So let me do 16 to the power of x plus 3 equals 64 to the power of 5 minus x. Okay, so something like this. If you're one of the people with a thumbs up there, maybe have a go at this ahead, try and work ahead of me here. But first, what I'm going to do is I'm going to look at this and I'm going to say, do they have the same base? No, they don't, so I can't equate powers yet. Okay, do they share some sort of base that I could rewrite them as? Yes, this one here is 4 squared, this one here is 4 cubed, so I'm going to rewrite those. Maybe I'll use red. So this is 4 squared to the x plus 3, and this is 4 cubed to the 5 minus x. And I'm going to multiply powers here. So we're going to have 4 to the 2x plus 6. And this one's going to be 4 to the 15 minus 3x. Now I'm ready to EQPs. And so I'm going to set 2x plus 6 equal to 15 minus 3x. So I'm going to have 5x equals 9 and x equals 9/5. Okay, so what are we doing here? We're getting everything to the same power before we begin, and then we're just equating powers using that trick. Okay, so that gets us as far as this far to the right, but then we come against problems like this. Okay, and a problem like this is unfortunately not going to be able to be solved by an approach like this on the left. The problem is 250. It doesn't matter how you try these things. 250 cannot be written as 10 to the power of anything, and 10 can't be written as something else to the power of something. 10 isn't the same as 3 cubed or anything like that. Nor is 250. So we can't write these two things somehow to the same base. And so this is where we actually use a button on your calculator that you probably haven't used a whole lot before, but is one of the more important buttons on calculators, and that is this log button. Okay, so I'm just going to very briefly, introduce this at this stage just as a really straightforward, simple process. We are going to talk next week, late next week, a little bit about logs and what they mean and what they do. But for now, I'm just going to show you this process here as a sort of a real crank the handle algorithm. Okay, so we have 10 to the power of x equals 250. It turns out that that can actually be rewritten as x equals log, and technically we write a little 10 there, but you quite often just leave the 10 off, of 250. Okay, so this statement below is actually just an equivalent statement. It's just a rewriting of this here, right? So 10, putting something to the power of x and equaling it to 250 is exactly equivalent, just written in a different way, to x equals log to base 10 of 250. So what does this statement here mean? It means x is the number that you would have to raise 10 to get 250. All right, so let me show you how that works on a calculator. Now, different calculators ask for you to press the buttons in different ways, so you might have to experiment here a little bit. But if I just write 250 here and then hit my log button, it tells me straight away what power I need to raise 10 to get 250. So in this case, calculator says is going to be 2.39. You can keep as many decimal places or many sig figs as you like here. 7, 9, 4, ... And that is going to be x. Now, that log button on your calculator is always talking about powers of 10. So it's saying that literally, so if I type in here 10 and take the log, it's going to say, what power do I need to raise 10 to get 10? 1. If I put in 1,000, what power do I need to raise 10 to get 1,000? 3. And of course, if it works for nice powers of 10, then it's going to work for not nice powers of 10. So what power do I need to raise 10 to get 80? Well, we're expecting something that's 80 is bigger than 10, so it's bigger than a power of 1. It's smaller than 100, so it's smaller than a power of 2. It's 1.9. Okay, so that's what a log does. That's what the log button on your calculator does. It solves equations that are written like this. Okay, so maybe I'll just write one more example there, but there's nothing a whole lot going on here. Let's go 10 to the 3x minus 5 equals 1,200. All right, so you might say, oh God, how can I possibly do that? Well, we use logs. So 10 to the power of what gives us 1,200? Well, we use our calculator here. We say 1,200 log, and it says the answer is 3.079. So the watt power of 10, our calculator tells us that the watt is 3.079. And then we say, oh, wait a minute, what was the watt? The watt was 3x minus 5 equals 3.079. That means 3x equals 8.079, which means x equals 8.079 divided by 3 equals whatever it equals. Add 5, divide by 3, we get 2.69. Okay, so this log thing, what it does is it says for equations involving powers of 10, only powers of 10, it lets us just skip all the steps that we'd normally do. Okay, so I've said increasing complexity, but it's actually kind of the least complex because it's just something you can just plug straight into your calculator. Okay. Now we have the last one, or the last one on this page at least, which is same problem. We have two powers here. They can't be written to the same base, but it's also even worse because it's not a power of 10. So we can't just use the log. We can't just say, okay, well, 17 log, because that's telling us 10 to the power of 1.23 equals 17. We want to know what power we need to put on a 3. Okay, so it's a slightly harder problem. It turns out we're going to be able to use the 10 idea, though, as one little, we're just going to have to extend it a little bit. And the trick here is we're going to write both the 3 and the 17 as powers of 10. Okay, so what I'm going to do is I'm going to write 3 to the power of something equals 10. And I'm going to, sorry, no, I'm not. I'm going to write 10 to the power of something equals 3. And I'm going to write 10 to the power of something else equals 17. Okay, hopefully you can.
The 2016 movie directed by Dave Doremus, starring Kristen Stewart, Nicholas Hoult, and Guy Pearce.
I'm not sure if you heard that, but my phone just told me about a film called Equals, starring Nicholas Hoult. I'm not sure why. Thanks, Google. Okay, so we're going to rewrite this 3 and this 17 as powers of 10. And how do we solve this problem? Well, we just learned how to do that. So we're going to write question mark is going to be log of 3. That's 0.477. So we can write 10 to the power of 0.477 equals 3. And we can also take the log of 17 to find out what this question mark is. So we're going to go 17 log, and we get 1.23. So we go 10 to the power of 1.23 equals 17. And then what we're going to do is we're just going to plug both of these back into this equation up here. So we're going to get, let me just, we're going to get 10 to the power of 0.477, and we're going to get 10 to the power of 1.23. And then finally, we have two things that are both to the power of 10. Excellent, that's exactly what we want. So we can equate powers. So we can say 0.477 x equals 1.23 to 3 sig figs. And we divide through and we get x on its own. And we are finally going to be done, except I can't do that in my head, so I'm going to whip out the scientific calculator. So we're going to divide that by 0.477, and we get 2.58. Okay, so that's a bit of a mess of algebra, but let me just sort of walk you through the solution strategy that you should be using when you're solving exponential equations. First off, just identify, is this just a straight power? Can I just put my base to a certain power and find out and just guess what that is? Can I do this by inspection is what we call it. Next step, can I write the right-hand side as the same base power as the left-hand side and then equate powers? Okay, if you can't do that, can I write both sides to the same power, regardless of whether it's one of the powers that's already there, like in this case, or in this case here, is there some lower power that we can put both bases to? Then I'm going to equate powers. Okay, no, I can't. My bases are too ugly on both sides. Then you think about using a log. So if it's already to a base 10, then you can use a log to base 10 to solve it. And any equation that looks like this can just be rewritten as an equation that looks like this and can be done directly on your calculator. And then very last case, when you don't even have a power of 10, you don't have a nice base, everything's ugly, everything's horrible. What you want to do is put write both of these powers, both of these bases as powers of 10. You do that using the log method from before. And once you've done that, you rewrite them and then you can equate powers. Okay. I'm just going to give you a couple of minutes to sort of catch up on your thinking and your notes there. And then we're going to do one last type of problem, which kind of sits a little bit aside from these ones, but for whatever reason, textbooks love to ask them. So I'm going to show you how to do those ones as well, so they don't cause too much pain later on. Somebody just asked in the chat, thanks Rishi, is this video going to be on the classroom? Yep, so I'll upload this video. I've been posting the links. I've got a YouTube channel that I put them up to. So yeah, I'll post the link on the classroom and I'll also post it on the Discord. Yeah, so I'll also, I think I might also, well, you let me know if it'll be handy, but I might just take a screenshot of this page. Here we go. Oh no, I don't want to record. I just want to take a photo. Okay, when I work out how to do it, I might just take a screenshot of this page and post that up as well, because this sort of takes you through the different cases that you might have to solve. Okay. Let me know with some thumbs whether you're ready to move on to the last example, or you still need some time. Okay, I don't see any thumbs down, so let's do one last example. And that example is something that looks at first glance really, really tough. And that is a problem like this. So you've got exponentials, they're all being added together. They're maybe to different powers, different bases, although these are all, they kind of look like fours, but then there's this bit that's not, and oh God, what on earth do we do? Okay. Now, the trick to a problem, now, I do not know why, but the people who write textbooks freaking love questions like this. To be honest, they're not something that comes up a whole lot in. I'm interested in maths for solving scientific problems. So for me, it's a bit like, oh, what's the point of this? This doesn't come up in physics. But that's not quite true. There is actually one place where it comes up. So maybe I shouldn't be so dismissive. This comes up when you're solving Schrodinger's equation. So a problem like this looks really difficult. But the trick is to sort of observe that this power here is double this power here. And also that we can rewrite this in a very sort of evocative way. And let me show you that. It might not be that evocative to you. Okay. I don't know how evocative you found that, but I find it deeply so. The reason I find it deeply evocative is because I'm going to take this 4 to the x now, and I'm going to do something a little bit tricky, which is a trick that you're going to come across a lot over your maths career over the next few years, which is that I'm going to apply a technique called substitution. So substitution. And the substitution I'm going to make is I'm going to invent a new pronumeral. I'm going to call it A. It doesn't have to be A. It could be anything. I'm going to say A is equal to 4 to the power of X. Okay, now at first that's going to seem like a nothing burger of a move, but I promise it's going to be a really useful move. So then I'm going to take that equation above and I'm going to replace all my 4 to the X's with A's. Now, some of you might be starting to see why that's actually a really useful thing to do. Because we've just taken this horrible thing, which is an exponential equation, and turned it into a quadratic equation. So we've actually, in year 9, you've spent a bit of time solving quadratic equations like this, solving them by factorizing. And you can actually do the same thing with this substituted version of our exponential equation. So I'm not gonna revise how to factorize with you guys because, frankly, it's only for the sake of a couple of questions that you're doing this anyway. But also, this is something you can look back at from your year 9 notes, or maybe look up on YouTube if you don't remember. But remember, we're looking for two numbers which multiply to 64, but which add to negative 20. And because I invented this problem, I know what those two numbers are. So I'll let you work them out for yourself. If you want, I'll give you maybe 2 minutes. But I should have just pretended I could do it in my head, actually. Damn. Opportunity lost. Okay. I hope maybe you've thought of them yourself. But the two numbers we're looking for are going to be negative 16 and negative 4. So when we multiply out these brackets, we get 16 times 4, negative times negative, so that'd be positive 64. When we multiply out the cross terms, we'll get negative 16a and negative 4a. So they're going to add up to give us negative 20a, and then the a's are going to multiply together to give us a squared. So those two are going to do the job. Then we're going to apply null factor law. We're going to say if all of this is equal to 0, then one of these brackets has to be 0. So that means either A has to be 16 or A has to be 4. Then we're going to pull this move in reverse. We're going to come back and we're going to replace A back with 4 to the X. And at this point, it's possible we'd have to use logs or something here, but luckily we don't. This is actually one of the simpler cases from before. So we can just say, oh, X has to be 2 or X has to be 1. And you can go back and prove to yourself if you want that if you plug in X equals 2 up here or X equals 1 up here, this whole equation here is satisfied. Okay, that right there, if you can follow all the way through all of those with all your different solution strategies and a problem as difficult as that at the end there, using that one little trick, which is this substitution here, then you are going to be absolutely fine for this week's work.